So yeah, I'll be talking about reduced quadrature rules and some different kinds of applications. One is NURBS, another is reduced order models. These are completely different topics, but I'm using the same general algebraic approach to construct these sparse and reduced rules to accelerate the computation. So the outline first, I'll introduce our algebraic approach for setting up constraints for an integration rule and how we solve that with the non-negative squares solver. Then I'll show these applications for that we're using NURBS patch quadratures and also local standard finite element space rules in the context of reduced order models. So first, the general idea of this is we're starting with some typical quadrature rule where we decompose an integral over the domain into a sum of elements k. They could also be NURBS patches, and we'll get to that in a moment. But usually in MFEM, we integrate element-wise with some element-wise integration rule that consists of some set of quadrature points x sub i and weights w sub I. And we usually choose these to be exact for a certain described polynomial order that we're using in our finite element space. But in some cases, we end up using not the entire polynomial space of that order. If we can restrict to a subspace of fewer basis functions, then it turns out you can get a sparser rule. You don't need as many quadrature points if you're not using all the basis functions of that order. So that's something I would get. And the way we do this is algebraically by setting up a system of constraints that say we want to accurately integrate some set of basis functions rather than all functions of that order. And this is a general algebraic approach that can be used for any basis or quadrature type. So to make the ideas a little more concrete, let's look at the most basic example of, say, rectangular tensor product element where we have a tensor product of 1D integration rules. As you can see here, we can take this rule with 2 points in 1D, and you get 4 points in 2D. That's exact for order 2 polynomials. Everybody has seen this kind of thing before. What if you only want to integrate constants? Well, you already know that you can just use a single point. You could take the midpoint. You could also take one of these existing quadrature points. So A here is this a distance from 0. So you could take one of these existing points, and that would be like finding a sparse solution to this constraint system where we impose that just the constant function is integrated exactly. So this is one equation for one basis function that's a constant. You solve this underdetermined constraint system and say you could just take 1 as your weight for that one point. So you reduce the number of quadrature points and also change the weights. Similarly, you could do this for a non-constant basis function, say the product x times x. You can still get a single point with a different weight. So if you were to take a point on the left side, you get this weight 1 over 3a squared. If you flip it on the right, you get this different weight. But the point is, you can do this for any particular basis function. You can do it for a small set of basis functions and still get a smaller number of quadrature points, more than one, say, but not a set of points. That's the general idea. And once you formulate this underdetermined constraint system for the quadrature weights, you can solve it with this non-negative least squares algorithm. I won't go into details of this, but it basically is an iterative method that tries to construct a minimal set of entries for the solution vector that have non-zero value. So you want most of those entries to be 0 That means you can skip those quadrature points and do a lot less computation. So it computes a non-negative solution, mostly zeros, hopefully, and the other is positive. The positivity ensures that you get positive definiteness for a linear tone. And although it's possible that sometimes the weights might be negative in reality, we end up with these approximate rules that are always have positive weights. As an alternative to NLS, you could use linear programming. That's been studied by Masayuki Yano at the University of Toronto. But in his experiments, he's shown that NLS is even more robust, and that's what we've chosen here. MFEM now has a serial implementation, which is fine for the NURBS patch examples that I'll show in a moment. But we also have another library for use it's called LeBron that has a parallel version using scale pack. And I'll show examples of that later that are applied to the global space. So first, a very brief introduction to NURBS. I won't properly define what NURB spaces are, but just try to give you the idea. They can represent curved geometries very well. You can represent conic sections like cylinders and spheres exactly. You get high order tensor product bases. So this is similar to the context of partial assembly, where you use tensor products, and we'll measure that in a moment. You can have any number of elements within a patch, and they can have different kinds of spacing formulas, like I've shown here in this pipe example. And this animation will show you what the basis functions look like associated with the vertices, the edges, and finally the interiors of the elements. You can see that they're smooth. They can span more than one element. They have overlap. That's that can span multiple elements too. So they're tensor products, so they come from 1D basis functions. Here's a particular example where we have order 3 polynomials on 4 elements. So the elements are defined by knots, and here they're uniformly spaced. When we get these 7 basis functions, which has limited overlap, but some of them span multiple elements and overlap with multiple elements. They're also very smooth, as you can see. The smoothness actually depends on the multiplicity of the knots. Here's another example of NURBS 3 basis on 4 elements, but it's different. The difference here is that the knots have higher multiplicity, so we get less smoothness across the element interfaces. What I'm trying to illustrate here is that there are different choices that could be made for the NURBS basis, even of the same order, the same number of elements. And then it's an interesting question: how can you construct a minimal quadrature rule with a minimal number of quadrature points with a patch? Usually what we do is integrate element-wise, so we would just use an element-wise rule on each knot span. But here we're going to be looking at constructing a minimal rule algebraically, because there are too many combinations, and it's a difficult problem of how to do this theoretically. This happens to be the same number of basis functions as the Lagrange space. So we'll be doing patch-wise quadratures here instead of element-wise. This idea was part of a project with core form that we did with Thomas. We're continuing that work now, and we merged this PR 3088 last year that introduced patchwise integration. So instead of doing element-wise assembly, you can assemble an entire patch matrix for all the dots on the patch. And I'll show that that's more efficient. So we can do this patchwise matrix assembly, even partial assembly, using exact integration, and it's optimized with some factorization and taking into account the minimal interaction of the basis functions. And we also do reduced quadrature rules. You basically saw this slide in the first two talks today, which is just introducing some factorization, which is used in partial assembly. Instead of a dense matrix assembly, you can just do a series of 1D contractions. This reduces the complexity of the operator multiplication. And we also use this idea in a matrix assembly, but show in a moment. So the NURB spaces, as I showed, can have fewer basis functions per patch than, say, Lagrange elements. And then because they're smooth, sometimes we can take fewer points. This idea is not completely new. So there's been work, for example, by Hughes and his co-authors, where they present how to efficiently assemble the matrices with NURB spaces using the sum factorization idea. But here we're also computing with reduced rules. So this is a new addition. So what we do is in the matrix assembly computation, each basis function gets its own integration rule. So this allows you to really minimize the number of points used for each integration. Instead of using one rule for the entire patch, we can compute a minimal rule for each individual basis function multiplied by the other basis functions and 1D. Taking advantage of the tensor product structure, and then we compute these reduced rules on the fly for each patch, each dimension, and each basis function in 1B, corresponding to a matrix row. So here's an example where we had two patches. Looks like they're 64 by 16 by 16, and we had order 8 elements. So round truth integration rule element-wise would be for order 8 for the diffusion integrator. And if you do element-wise matrix assembly, like before this PR, it would have taken 274 seconds. And if you do just the full integration with optimization based on sum factorization and the limited interaction of basis functions, you can do patchwise matrix assembly much faster, 50 seconds. And this scales for larger problems too, with about the same factor of speed up. And the L2 error is on the order of machine precision, of course, because it's just a different order of operations. It's round out there. And now, if we use the reduced rules in 1B for each basis function, we can get further speed up. It's only 32 seconds for the patchwise matrix assembly. And with the error introduced by this sparse quadrature rule, it is negligible. We're still about on the order out of the round off the error here. And for fun, I also show the patchwise partial assembly. We're looking at the setup time, so this is not really fair comparison. For PA, the bottleneck comes the solve time, not the setup time. But you can see that at least the fact-wise matrix assembly is getting closer to that minimal amount of setup that's used by PA. And the error that we get from these sparse rules is essentially negative. And here on the right, we can see an example of the reduced rule where we took the full element-wise integration weights for 20 points and no less, and ended up calculating only 8 non-zeros. So this was a representative example out of the many reduced rules for the many basis functions in 1D, where we reduce the points from about 20 to 8. So this is giving a very good reduction in the number of quadrature points in 1D, and with the tensor products, it's even more. And this setup time actually includes the time to construct these rules on the fly. So we actually set up that constraint system and solve it with NLS during the matrix assembly, and that time is included here. The 32 seconds. So that's the NURBS part of the talk. Now we're going to switch to use order models, no longer in NURBS space, just standard finite elements. And so let me give a very brief introduction to these useful order modeling you're studying wrong. This is a data-driven vector-based approach where we take some high-fidelity simulation data for your last or your favorite MFEM application or mini app. You take solution data snapshots and collect them and compress them with the SVD. So this matrix on the left, W sub I, comes from solution snapshots as column vectors for different simulations using, say, different parameters of the simulation. And the goal is to construct a low-dimensional subspace that accurately represents the span of solutions over that range of simulations for a range of parameters. So we do this just by taking the singular vectors associated with the dominant singular values. And if your simulations are very similar, or some range of parameters, you will get a very low dimensional subspace. For example, the finite element space might have no unknowns, hopefully in use on like 10 to 100 basis vectors. So once you project to that low dimensional subspace, you can then run a simulation using the original code, but restricted to that subspace, and use an approximate solution that was attained using the original code and not some neural network. So it represents the physics more accurately. And this is done using our open source library, LibROM, for reduced order models. You can find it on GitHub here. And we also have a Python version. So when we get our reduced subspace, we can set up a reduced equation in the following way. We take some governing equation like this one, where the right-hand side F is nonlinear. It represents the finite element discretization in the MFEM case, and it's of some full order dimension capital N sub S, but we've computed a low dimensional basis phi, a very small dimension N sub S. And we use this solution approximation. It's some offset vector plus the reduced basis times reduced coordinates, W hat. So typically, as I said, is you might reduced from, say, 1 million unknowns in the finite element space to, say, 10 to 20 reduced basis vectors. So you get a very tall gauge to represent that. And once you do Galerkin projection into that low dimensional subspace, you can project and propagate with some time integrator. For example, if you use Euler time integration, it would look like this. But the problem here is, although you're in a small subspace, you still have this nonlinear term evaluation, which spans the entire domain, and it has full ordered complexity. So you don't get speed up unless you can reduce that nonlinear term evaluation. And we do that with in this talk by using this empirical quadrature procedure where we reduce the integration rule. So this has been studied by some authors before in the past. We're applying it to the MFEM Lagos in this work for the first time. But it's been studied by Barhat's group, where it's called ECRSW. Iano, who I mentioned before, has done this with DG finite element formulations. And we get a sparse quadrature rule as in the NURBS case, but now we're setting up constraints that say we want to integrate some non-linear weak form like this, where we have a non-linear operator of the trial function times some initially linear operator on the test function. So using this, we can set up our constraint system that's underdetermined, saying we want to integrate some reduced basis vectors, say BJ, from our reduced space times solution snapshots in the non-linear term. It's not sufficient to just use the basis vectors in the non-linear term because it's non-linear. So if you include a rule that satisfies it just for those, you don't get the entire space because of the non-linearity. So we put a large number of solution snapshots U sub I into the non-linear term. For example, one snapshot per time step from the offline training set simulations. And this gives a rather large system of constraints where we can an integration rule. But we can solve that with the parallel version of NNLS that we have in Redron. We applied this to the Lagos mini app. Here we have three unknowns: velocity, position, and energy, with these conservation equations and an equation of motion. We saw some examples of Lagos in previous talks. Basically, we compute a reduced space for each of those three variables. We get reduced mass matrices in this way, and the key for this talk is we have to reduce this non-linear evaluation on the right-hand side, and we're doing that with reduced quadrature rules computed by NLS for those snapshots. Okay. Of course, this is an convection-dominated problem. So if you were to do this for the entire simulation where the solution changes the domain, you would end up with a large number of quadrature points still. So to further limit the size of the basis and the rules, we're doing this on small time like those that partition the time domain. Well, here's that set off last example. You can see the velocity magnitude on the left and the sampled elements on the right. So this is showing you that the NNLS reduced quadrature is taking weights that are where the computation is. Right? See, it's following the shock front there. We reduce the number of quadrature points from 32,000 on average over the time. If the windows to about 94 on average. If you just use the reduced space with the full integration, the error is about 2 times 10 minus 5. If you put in the reduced integration rule, the error goes up only slightly to 3 times 10 to the minus 5. So still very accurate. This is a reproductive test on the same simulation that we trained on, but we also have predictive tests with good results. I'm not showing those here in the interest of time, but this demonstrates that you still get good accuracy with that sparse reduced rule, and the speed up is pretty good, but 36 times here. This is a small problem. If you go into larger problems, there's more potential for speed up. I'm running low on time, so I'll go fast through these examples. Here's the triple one, which is low order, and you get 9 times speed up with, again, very good accuracy. If you raise the finite element order, you get more speed up, 22 times instead of 9. So larger problems, higher order, larger mesh, gives you more potential for speed up by eliminating more elements computations. So is the good speed up and accuracy for all these problems, as well as 2D ratio tests. Of course, in 2D, the speed up is not as good, only 2.5. As I was saying, it helps to have a very large scale problem with high order ISM machine. Finally, if you used any of these bases and these quadrature rules, there is some error incurred, and one side effect of the error is that energy conservation is no longer maintained. It's well known that the RK2 average scheme for Lagos conserves the discrete total energy exactly. But that's not true once you introduce ROM. But we've shown that under some conditions which are easy to implement in the ROM formulation in the time stepping, if you just ensure that that consistent approximation is used in the 2 conservation equations, this is what assumption 3 is saying, basically, then you can still conserve energy exactly. And we see that if we use this conservative EQ3, we conserve to machine precision, whereas the basic EQ3 had considerable change and the energy. All right, so finally, to conclude, we applied the same approach in different ways. One to matrix assembly, the other to explicit time stepping, where we're evaluating expensive right-hand side. But we use the same generic algebraic approach, so we don't have to figure out in particular cases. We can just do this in an automated way. We can also satisfy some physical constraints like conservation, and we saw a great speed up without losing much accuracy. And all of this can be reproduced using our open source code in MFEM, the ROM branch of Lagos, and our library for reduced order models. So thank you very much.